Good morning and welcome to Rigaku. You're in our applications lab here. We're actually right across from the picture you see on the slide here. We're in Houston, Texas. We're actually in the Woodlands, just north of Houston. And this is our everything X-ray lab. And we're specializing in X-ray fluorescence. That's what Thanh and I, our jobs are, to work on applications for fluorescence. I'm Glenn Williams, by the way.
And I'm Thanh Nguyen.
So, and today we're going to talk about direct analysis of intact pills by XRF. Essentially what that is quality control of API potency or excipient blend uniformity, heavy metals, impurities, but without having to prepare a traditional type of sample, which may be grinding. We'll talk about that in a little bit, but it'd be grinding into a, puck, or pressing into a puck then and analyzing, a set. But what we're going to show here is analyzing everything as a final product without having to really do any prep at all. Okay, so there's a lot of applications in the pharmaceutical industry where XRF has a place. It has not been widely adopted. It's just that the education for what's available, or really understanding, because there's such a wide variety of instruments that Thanh will talk about in a second, it hasn't been adopted. And so what we're doing is trying to help educate, and we have several sessions here. One talking about analyzing catalyst residues in like a discovery type setting, or process control, process chemistry, and catalyst poisons. We have a session coming up on salt conformation, so doing carbon, nitrogen, oxygen analysis. And then, in this excipient blend uniformity, we actually have a session we're devoting kind of to formulations as well. But what we want to focus on in this session is USP 232. But keep in mind that this direct analysis technique could be used on, on other things. It doesn't have to be just for the heavy metals analysis. So just a quick 1 minute, just information on how does XRF work? How is it able to analyze for these elements or metals in my sample? I will give a 1 minute overview, but if you can come to our session at 2:30 Central Time, then you can see a little bit more. We're going to talk about, we have a 90-minute session. We're going to talk about some of the theory. We're going to actually do, prepping calibrations and
running real samples, right?
Okay, so how does XRF work? Well, we're using X-rays to generate fluorescent X-rays in samples. We have an X-ray tube that produces a polychromatic spectrum of X-rays, and that will excite the elements in our sample, producing fluorescent X-rays from them. How does that work? Well, what we're doing is we are using those primary X-rays. If they're of sufficient energy, they will kick out inner cell electrons. Those will be lost as photoelectrons. And then what we're doing is there's an unstable state left behind when those inner cell electrons are kicked out. The outer cell electrons, which are of higher energy, they will fill that to create a more stable state. When they fill and drop to a lower energy state, the difference in energy is lost as a fluorescent X-ray. And this is what we're interested in characterizing and quantifying in our sample.
Okay, so as you can see here, there are a lot of different XRF instruments that Rigaku has, and there's actually more that we can't fit into this slide. So it could be confusing. So we're going to distill this down to show you which instruments are applicable for this application. Okay, so these are the particular instruments that we have that are currently in use in the pharma industry, ranging from the floor model all the way down to the benchtop system. And so we have the Primus 4 and 4i, which are the 4 kilowatt system.
And those can pretty much be used for like every application. And then it's just kind of like ones that are for subsets of those.
Right. And then we have our 3 kilowatt system, which is a Primus 3 Plus, and then we go down to our benchtop systems, all the way to including our ED as well. But in this particular application, we're focusing on the floor models, which can do a lot of the ICHQ 3D levels. the Primus 4, Primus 4i, and the Primus 3 Plus.
Okay, so for ICH-Q3D, there's a couple different approaches that companies can take to analyze. You can look at just drug substance and excipients. You can do summation techniques. You can look at final product testing. And that's actually what we're going to be focusing on this, where we're actually doing final product testing, but doing it not only on the final product, but literally on the final product in its final product state.
As a pill.
As a pill. So elemental impurity testing has been around for a long time, but there's very old methods. And recently, and when I say recently now, it's probably about 3 or 4 years. At this point, it's been implemented. Previously, it was wet chemistry methods, so precipitation methods, very old methods, and so it was updated for some more modern techniques. The focus of that initially was ICP-MS. In fact, there are issues with those techniques that have to be dealt with in terms of digestion and things like that. And a lot of those things are being worked through, but there's also alternative methods that are possible to run, such as XRF. And so that's one thing we're trying to help educate, what the possibilities are. The focus of this method is to look at the required testing elements, which are your class 1 and 2A, your big 4, and your 2A.
You can easily add in these other classes as well if your product requires you to test them.
Right. Okay, so permitted, you might see PDE or permitted daily exposure, and we're going to talk about the daily dose level that we're testing to. Essentially what that's referring to is the fact that you may have a product that, and not just talking about the active dose level, but what's the size of the pill? How many pills do you take in a day? So in other words, how much are you eating of this material? And so how much are you ingesting and then getting exposed potentially if there were heavy metals in the product. If you have smaller amounts, we can have a higher concentration that's permitted in order to still be within the allowable limits. If you were to take, let's say, 20 of pills of this size a day, you're going to have much lower concentrations that you're testing against because you are exposing yourself to potentially more of that. And so that's what we're referring to, that daily exposure or concentration limit.
So before we get into that, let's talk about sample prep. How do we prepare this in order to build our calibration? So what we did here is we took some ICP standards of the class 1 and class 2A, then made a cocktail out of it at a 5x concentration above what we were shooting for. From there, we would add 1 ml into what we're using here is blank powders, which is actually just cellulose to mimic the excipients of the material. We make it 5 grams here, spike in these concentrations, and then from there we would dry it in an oven or a vacuum oven. After it's dried, you would just cap it and mix it about 5 minutes thoroughly, and then just pour the entire content into this dye assembly and press it into an actual pellet or a puck. And then from there you would just directly analyze it. So you have a bigger surface area, a bigger amount, as you're analyzing the entire thing.
And another point to make here too is that this looks kind of involved. And if I was doing this on something like an ICP, where I'm having to do this every single day, every single time I go to run a set of samples, yeah, I wouldn't want to do this. The nice thing about the XRF, and we'll talk about this in a couple of our sessions, as well as our workshop later today, is that you only have to do this once. You do this to set up your method, and that method could be good for years. In fact, we have this machine behind us here is about 5 years old. We still go and run our ICH-Q3D methods that we've created and still get results within spec 5 years later without having to do any kind of calibration. So that's a really major point to make.
That's key, and it's not, like compared to chromatography or LC-MS where you're doing the calibration every day before you run the unknowns. This you do it once, and then the method is saved on the system. From there, you would just go and make your unknowns and check it.
Right. You might have a system suitability material or something that you're just doing a check to verify you're still within spec.
So now we're going to show you the data for the 1 gram max daily dose that we've followed the guidelines for to do validation, basically.
The idea for doing 1 gram daily dose is that for a 1 gram daily dose, it covers most prescription pharmaceuticals. 5 gram daily dose, almost all of them. Some of the examples that are given are a 10 gram daily dose. It becomes more difficult for an instrument like XRF as we go up to higher and higher maximum daily dose levels. So something like Pepto-Bismol or like a calcium carbonate type material that you might be having, like an anti-acid. If you're taking 10 grams, 100 grams of something like that in a day, you're going to have much lower concentration limits. In those cases, those are going to have to be ICP techniques. But we're going to focus on where there's a big convenience for and a system that's kind of meant to do quality control analysis. There's an advantage for looking at most of your materials that would be in this concentration range.
As you can see here for the class 1 and class 2A, all our calibrations are linear because we spiked it. And also you can do the overlap corrections, particularly for lead and arsenic. So you just use like different lines, and then the software can also do apply the correction as well for you. Right, so as you can see from the previous slide with the calibration, we're just summarizing the data here for our quantitation level, our range, and our linearity. So we're following the 232 guidelines at the 1 gram daily dose, and you can see it correlates very well with very good linearity at least 3 nines for all of the class 1 and class 2A.
And you see our limit of detection based on the actual analysis time and how we set up the methods are well within what our quantification limits need to be.
Right, and if they need to be lower in XRF, you would just count longer.
Or use a little bit higher power or whatever, so we have options.
Our next one is showing the detectability for the all these elements, and so the requirement was to distinguish the difference between the 0.8J and 1J level. And you can see here it meets all the criteria.
So these are all listed within USP Chapter 233, which are what are our basically our validation requirements. So TON has actually done that on several different materials, really showing that the XRF is will meet these criteria.
Right. So I was in a GLP lab environment in my previous job, so following these guidelines were not as difficult. It's just a matter of creating the press pellet and spiking the levels and then just running this and it meets the requirements really easily actually. And then here, the next one here is showing the accuracy. So the acceptance criteria was just the spike recovery should be between 70 to 150% of the mean of 3 replicate preparations. And you can see here, it's very, very good recovery, close to 100% for all of them.
Of course, that makes sense. It's a direct analysis technique.
Right.
We're not digesting material, so you're really not extracting or
right, and
you're
like analyzing the full pellet too. So there's no loss because you're spiking it in. You're taking the entire material and then making the press pellet. And the precision here is quite low as well. And the next one here is the repeatability. So this shows the instrument repeatability of analyzing it multiple times, so 6 times actually. You can see here, again, the repeatability is really, really low.
Well within the 20%
much lower,
RSD requirement.
And ruggedness is where we analyze on different days. Different analysts on different days. Okay, again, it's very stable, very rugged, so it is easily achievable. With the requirement being less than 25% for the RSD. And the specificity showing that there's no overlaps or
if they are, we can account for
different
those.
lines.
Yeah.
Right.
This is, and what we did in this case, so we did it in two different examples. Specificity here was we took a separate pellet, and then we essentially have them spiked with only one of the elements at about 100 ppm level. Now you'll see everything else is below detection limit in that single pellet. So we have a single pellet with mercury, a single pellet with cadmium, none of the other elements in it. And when you run those against the method, all it's finding is just that element. what you'll see here is that some of them are a little bit off in terms of the quantification, but that's because our quantification level, if you remember on our summary slide, was in a much more narrow range. If we added standards up at that higher level, we're going to get, this is just to illustrate though that you can see those elements, you have specificity.
And visually, we're showing here that there is no interference from one element to the next. You can see there's clear separation.
If you look
on
at the
those.
whole spectrum.
Right, right. And if there are overlaps like lead and arsenic, you would pick a different line, which is easily can be done through the software. And here's just showing it visually again here, especially for, these are the two that would overlap in this class 1 and class 2A elements.
Yeah, if you're curious how that's done, join us at 2:30 Central Time.
That's right. Okay, so now that we did 1 gram, how did we do in the 5 grams? So the data here is very similar to the 1 gram daily dose.
Just the only difference here is our concentration limits, right, are more stringent. So we have to go down to lower levels, and this is proving that even at a 5 gram daily dose level, we can meet those requirements.
Right.
So those are the requirements. Those are the levels of our standards. And then these are the calibrations.
Right, so it's very similar to, we're not going to show all the data, but we know that we're able to meet the 5 gram daily dose. And again, the linearity is very good.
This is an instance where you might have a coded tablet. And it's an advantage why we're showing the WD system here. And the fact that, you know, we can resolve peaks. And if there are overlaps, we can switch to a different element line. So in the case of something that has high amounts of titanium from a titanium dioxide coated tablet, we can switch to the vanadium K beta peak, which still has good signal and actually good linearity there. So traditional prep would be to take a bunch of pills, pellets, and grind those up, as Thanh was showing and how we made the standards, press those into one puck, and then run that puck of 90% of the area of that puck on the machine, and get your result. Still very easy, no digestion. It's still a direct analysis technique. It just adds an additional step: grinding, pressing, and then mounting into the holder and running. The desired prep would be, hey, can we just take these pills and run them as is?
Right.
And so that's something that we decided to investigate. And with the elements for ICHQ3D, we thought, hey, there's a chance. If you get down to the lighter elements, you need to have a good surface. And so what we wanted to see was, with the lightest element we're analyzing, vanadium in this, can we do this type of prep and still get good results and be able to validate it?
Okay, so basically we did the exact same thing as the prep that we showed before, but instead of pressing as a pellet, we went ahead and pressed them as little bitty pills. So we actually did this 1 by 1 by hand. So, because you can imagine.
You can do this much more easily if you have a small tablet press.
Right.
We're cranking one out 1 by 1,
right.
Which actually shows more variation because we're not doing it where it's a more constant, pressure and whatever that would be applied. We're doing each one individually.
Right, and once you get all the one concentration in, we just basically just poured it into a cup and then build a calibration using that in place of the big press pellet here. And lo and behold, we got good calibration.
Yeah, we expected we were gonna have to run it again, shake it, and then average those results, but we didn't. The first, just randomly how we put them in, and this is just a, picture of the, pills in one of our tube above cups. We have the tube below model that Thanh was showing on that first slide, the Primus 4 versus Primus 4i. Same optics, same performance. It's just how you would put the sample in. Well, it's convenient if we just pour them in that way, or this way. We basically have a spring that pushes them up. I think on the next slide.
Right. So what we did for the calibration was we did like little round pills.
Mm-hmm.
But then what if we have different size pills that are oblong, different shape? How will that affect our results? And what about orientation? How you put them in? Is there a particular way we need to, or can we just pour it in and analyze them as is?
So this was just looking at as we had prepped in the same dimensions, the same pill shape, etc. How do we meet the acceptance criterion. We're not going to go through a full set of those tables, but we pass validation, easily with this. And even this is at the 5 gram daily dose level, so at the 1 gram daily dose is even easier. We get more sensitivity. So we're able to do that at all the different validation requirements. Well, now we're looking at, as Thanh was suggesting, well, if we did those, as you saw in our calibration set, we made pills that are, the shape that we see here. But what about if we were to then run the same formulation, the same things, but run them as these kind of oblong shape, if I'm describing that shape properly? And what would the results be if we run it against the above pill shape there? Well, what we can see here is we're getting, if you look at the nominal concentrations from the top set, what they were made, but then the bottom are the pill shapes as we show there. We're getting all within the same acceptable limits, and we can validate that method with the different pill shape.
So the pill shape doesn't matter, basically, is the overall outcome for this. Then what about orientation now? So we also tested just laying it all flat evenly, or just laying it all on the side to see if there were any effects on this. And as you can see, we do not see any difference depending on how you put it in. So the overall conclusion on this is you can just pour directly into a cup, analyze them as is.
Yeah, so what you're seeing in that table there is a random orientation versus a preferred orientation, and what the differences in the actual result are. Same pills, same set. We've just actually purposely made an orientation.
Right. And here's shown the deviation from random versus preferred.
As expected, the only one that showed any type of deviation was the vanadium. That's the lightest element, so we expect that, because depending on how many void spaces there are, how rough the sample is, it will affect the lighter elements more than heavy.
So we have summarized all our data from what you've seen into this published paper in tablets and capsules. So basically, once you've created the calibration as pills, all you would have to do for your unknowns going forward is just go ahead and pour it into the cup and analyze them as is.
Yeah, so that, the ultimate goal is what you see here, and I think, that is definitely something that could work in many cases, and really worth it to pursue this technique if you think you're going to be testing final products.
And if you have any questions, please feel free to email us directly. I know him. But again, we would like for you to join us at the 2:30 workshop to see these us analyzing these samples directly.
Making calibration curves, talking a little bit more about the theory, so that'll be more in depth. And if you want to learn more about it, you feel free to reach out to us, and we're more than happy about your particular products and your particular needs to talk, even on a one-on-one or with your groups.